Hi, in this segment, I'm going to talk about the Affine Cipher. Although it's broken, it is worth to study this cipher because of the mathematical underpinnings that we would need for future videos. The algorithm goes as follows. The encryption process requires, let's say the encryption algorithm, right, would require two keys, right? The A and B are two secret keys, private keys, okay? Only the sender and the receiver would know A and B. And suppose Alice wants to encrypt a message X, okay? What she will do is she will compute the encryption of X as follows. Let's say X is one English alphabet, okay? Just one alphabet. It could be A, B, or anything. Let's assume A is encoded as 0, B is 1, Z is 25 as usual. So how are we going to encrypt? The encryption process on the Alice side will be A times X plus B mod 26. So because we are going to work with English alphabets, okay, English alphabet characters, there are only 26 of them. So we do mod 26. Okay, so just to be clear, X itself is just one number. Okay, X can be 0 or 1 or 2 all the way to 25. Okay, this is the encryption process. What about decryption? As you can see, we need to get rid of B first, right? Let me call this as Y, okay? So how will Bob decrypt that? Of course, Bob should also use the same A and B. Bob has to first get rid of B, right, from Y. So from Y, he get rid of B. He's getting rid of B. And then he has to get rid of A as well. But A needs multiplication. That means we need to do the inverse, okay? So that's basically it, right? This should give us the X, okay, in mod 26. Structurally, it's very, very similar to the CIF cipher, right? If we put A to be 1, then you have your CIF cipher, because in CIF cipher, all the input digits or characters are shifted by a fixed amount, B positions. Here we are multiplying it by A and add it by B, okay? There's one more low-level caveat I need to explain. A inverse may not exist always, okay? A inverse means, for example, let's say you have a number, let's say you have a number 5, okay? What should I multiply with 5 so that I get 1 in mod 26, okay? The number that goes inside the box, that's called the inverse, okay? Inverse of 5. So you may manually try it or apply any computer program out there. We talked about algorithms to compute inverse. It is part of this video segment as well. But let's say if you trust me, I would say 5 inverse is 21, because if you multiply 5 with the 21, you get 105, and you divide it by 26, you get 1 as a remainder. So you would need to be able to find the inverse, and the inverse may not exist always. So that is another thing you need to be aware of. Inverse only exists if let me now summarize the inverse property. Okay, this is our algorithm. We talked about encryption and decryption. Okay, how can we compute inverse? A inverse can only exist if and only if GCD, the greatest common divisor of A and 26, is 1. If A and 26 do not have 1 as the GCD, then it is impossible to have A inverse computable, okay? So I can prove that later, but you can take it for faith that GCD of A and 26 has to be 1, then you will be able to successfully decrypt your input ciphertext. We are assuming Y is the ciphertext, right? Y is the ciphertext, X is the plain text. If you have a string, you would encode it as numbers. For example, I'm going to show to you in a moment. Let's say I wanted to encrypt the word hot. How would I go about encrypting it? I will map H to some number, integer number, O to be another number, T to be another number, okay? And then I will keep calling this encryption function on the number. Let's say H maps to 7, 14, and 19, okay? In terms of treating A to be 0, B to be 1, and so on, you will have H to be 7, O to be 14, T to be 19. So you will call your encryption algorithm as follows. You will be doing E, right? And say you want to encrypt H. Okay, what else you need to do? You need to do, of course, it's same as encrypting 7. Okay, what will you do with the 7? You will encrypt 7, but you need A and B. Let's say my A is, for example, 7, B is 3. Let's say A is 7, B is 3. Okay, and now, of course, the A and B are the private keys, right? Only Alice and Bob would know this secret keys. So if you plug A and B into this formula and do A times X plus B mod 26, you can check for yourself. The answer will be, in the first case, 0, okay, for H. Similarly, for O, which is the next character, O is encryption of 14, right? So you'll be doing 14 times 7 plus 3, which turned out to be, if you trust me again, it turned out to be 23, okay, in mod 26. Okay, that's basically it. And then you can do the same for T. And during decryption, you will go backwards. You will first subtract B from your ciphertext and then multiply by A inverse, okay? And computing A inverse can be sometimes tricky, but for small modulus, it's easy. So you can try it easily with your hand. If you know Chinese remainder theorem, you can also break 26 into prime factors 2 under 13 and solve it in small groups. I talked about Chinese remainder theorem in other segments, but I just want to give you a connection there. All right, so that's basically how the affine cipher actually works. By placing A to be 1, you get back to your CIF cipher, and you need to make sure that A is relatively prime. Let me be more clear. You have to make sure that A and 26, the GCD is 1, okay? That means you cannot have A to be 2 because 2 GCD with 26 will be 2. So you can't do affine cipher when A is an even number, okay? That's an interesting property. All right. One more thing is that I will quickly show you a demo, right? And then we can wrap it up. Encryption using affine cipher. I encode the message string into numbers. So all of the string HOT will become a bunch of numbers. And then I multiply each number by key A, right? A has to be multiplied. And then I have to use the key B as in the regular CIF cipher. That's what I'm doing, okay? And the encrypt n is something that basically the function we talked about earlier, I can quickly show to you, is a regular CIF cipher encryption. So I'm basically reusing the CIF cipher encryption as it is. That's nice because it's a special case anyways. So the code should also have the same capability. Okay, and the decryption of the affine cipher goes exactly the same way. First, we subtract the key B, right? And I am doing the same here. You have a key B, and I do a decrypt n, which is same as the CIF cipher. That means you'll subtract the key B, and then compute the mod inverse of A, and multiply each of the numbers by mod inverse, and then I convert the number array into string array. Okay, so now let me start the Python code, and we'll show to you how the affine cipher can be executed. Let's say encrypt affine cipher, right? And I wanted to encrypt the word hot, and I need to pass A and B, 2 keys, right? I will pass A to be 7, B to be 3, and I get AXG. Let's decrypt now AXG, and do decryption. Hopefully I get back the hot. Okay, so I get back hot. By the way, I normalized uppercase and lowercase. That's the reason why you see capital HOT. All right, that's basically how the affine cipher actually works. The important takeaway is that your key A must be relatively prime to 26. If your alphabet set is 26. 26 is nothing special. You can generalize it to any other alphabet set. But I happen to use English, so that's the reason I said 26. Okay, but you can also do brute force. But let me briefly explain the brute force. The brute force idea goes as follows. You can try all possible A's and B's, right? What are the possible values of A? All elements that are relatively prime to 26, okay? There are only 12 such elements. So A cannot be even number, right? Otherwise the inverse won't exist. So A has to be odd number. So there are only 12 A cannot be 13 also, because 13 is a multiple of 26 is a multiple of 13. So there are only 12 numbers possible for A, and B can be any value from 0 to 25. So if you multiply, right, there are 26 possibilities. So it's a little bit more than 300, but anyway, for our purpose, that's not a lot of keys. Okay, A cannot be all possible A's, because A inverse won't exist. B can be all possible B's from 0 to 25. So total number of keys that you will be brute forcing is just 26 times 12. Okay, and if your ciphertext is sufficiently long, there's a high chance that the key that you find is the right key. Okay, so that this is not many keys. So that's the reason why affine cipher is actually not really used. Although the idea behind is pretty novel, that you can take a number x, multiply it by a and add it with b. In AES, for example, affine cipher is all actually used in some form. There, the numbers a, x, b are all matrices. Okay, it's a slightly different context, but the thinking is actually present in the historical classical ciphers like affine. Okay, later I will prove why the GCD of A26 has to be 1 for decryption to be successful, and also to have the function y equal to y equal to ax plus b as a one-to-one function. Okay, remember, we need to have one-to-one function, otherwise you can't successfully decrypt. Okay, thank you for your attention. That's all.